Okay, let's get started. We are doing Ruth Hurwitz, and we're going to do another example. So we saw sort of the procedure of setting up to do Ruth Hurwitz. The highest order S term. This does not wake up by itself. The highest order S term, in this case, is S4, which means we start with row S4 here. Then we proceed down S3, S2, S1, all the way until we get to S0. And we start to identify our coefficients. So in our S4 row, we grab the coefficient associated with S4. Then we skip. Then we go to the S squared term. And then we go to the S to the 0 term because we're skipping along. And then now we go to the S3 row. There's our 1. There's our 5. And there's no other coefficients. And so sometimes it helps to go ahead and put a 0 in there, because sometimes you see there's no number there and you think, okay, there's actually not a number. But anytime you need a number in any of these, there's no other term, so it's just multiplied by 0. So then B1, B2, C1, C2, and D1 are all calculated. Let's go ahead and calculate B1. So B1 is going to be the determinant of that row right above. So it's always in the first column, and the column just to the right of the coefficient you're solving for. And then the -1 is just from the methodology. The 1 term here is always in the first row right above it, okay? So we do that and we get -7. Now we're going to solve for B2, and notice 0, right? So you don't actually have to write it in there because it doesn't show, but it sometimes helps just to complete that. So you have -1/1 times the determinant. So let's see if I can do a color change here. Let's pick here. So it becomes a determinant of this here and this here. So it's 1, it's always the first column, and the column just to the right of the coefficient we're going to solve for. That's how I ended up with my value of 10. So I've got B1 and B2, so I stuffed those in my matrix, and now I'm ready to move on to the next row. So do that again. Let's pick a different color. So now I'm solving for C1, which means I move down 1 row, take the determinant of that, and I always take the element in the first column. So here's my C1 term, and I just get a fraction. No big deal, 45/7. I'm going to go ahead and solve for C2, which means I have to grab these two and these two over here, which are both going to be zeros, right? So when you have both numbers being 0, what's the result of the determinant going to be? 0, right? Because when I multiply, so I have -1/7 times 1/-7 and 0 and 0. Multiply 1 times 0, I get 0. Multiply -7 times 0, I get 0. So it just ends up being 0. And what happens is you'll start to notice that as we get to each successive row, we start dropping out a term, right? So we can see that we had 3 terms, then we went to 2. We have 2 terms of rows of 2, and then we get to 1. And then eventually, we only end up with 1 coefficient here. And if you'll notice, this D1 is that last coefficient term. So a good way to check if your results are correct, if this term here does not end up over there, you got a problem. You made a mistake someplace, okay? So that's a good way to check to see what you're doing. So let's solve for D1. So change our color. We'll go to blue here. I need the determinant of this. Notice I stuffed in the 0 there just to make it a complete matrix. And I just end up with my 10. So stuffing that in. Any holes in the right-hand half plane Does that reveal that there are any poles in the right-hand half plane? What's the rule for Ruth Hurwitz and if you have right-hand half plane poles? Or right half hand. We'll just say right half plane, just make it easier. But it means it's unstable, but how do you know the number of poles in the right half plane? Or right-hand plane? It's the sign changes. Plus to plus, is that a sign change? Nope. Plus to minus, is that a sign change? Yep. So that indicates that I have at least one. Minus to plus, is that a sign change? Sure is. 2. And plus to plus, is that a sign change? No, not a sign change. So I only have 2 right half or right hand poles. Let's check it in MATLAB. Does MATLAB tell you or agree with your results for the number of right hand plane? Yeah, because aren't these both positive numbers? Those are poles that when you do pole zero maps, plot in the right half plane. So in fact, MATLAB agrees with our results. Okay, any questions on that? All right, so let's pick a value and see about alpha, because we have to have 2. These are called necessary but insufficient conditions. We talked about these last class. Condition number 1, no sign changes in our quadratic, right? Or a polynomial, we'll call it a polynomial because it can be many terms. So all these numbers have to be all positive or all negative. So we know that alpha needs to be greater than 0, right? So have no sign changes. The other requirement is no term or coefficient vanishes. Okay. So what that means is that this cannot equal 0. If it equals 0, then that coefficient vanishes and you have at least one pole in the right half plane. So if you see a problem, and if I had this as a negative s cubed, and I asked the question, is the system unstable or stable? You don't have to do any work. You don't even have to plug it into MATLAB and do the roots. You just know it's unstable. So I see a negative there. It's unstable. Or if this didn't exist, 2s to the 4th plus 3s squared plus 5s plus 2, let's say, I know that that has an unstable system because this term vanished, right? There is no s cubed term. So those are the necessary, but they're not guaranteed to be enough. So that's why we have to do the Ruth Hurwitz. So let's take a look at a goofy example. What if we have a 0? So let's say this is s cubed, s squared, s to the 4th, let's say 1, 2, and I don't know, let's just call this 1, 2. And if we did our calculation over here, we ended up with a 0 in there. When we do our determinant, it might be okay, but the problem is you're dividing that determinant by 0, right? What is the result of dividing something by 0? It's undefined, it's infinity. So we can't have a 0 in that first column. What about if we have a row of zeros? If we have an entire row of zeros, we also know that 0, it's going to be indeterminate, but then we know that we're going to have 0 whatever. So that's even worse problem, isn't it? So we have indeterminate number, right? 1 over infinity, 0 is infinity, times 0. So we got a really goofy number. So we have to come up with 2 solutions. What's the first solution? If it has at least one non-zero term. So you have a 0 in the first column, but the other terms in that row have numbers, right? Or have at least have one number. Then that's called special case number 1. You've got a 0 in the first column. So what do? We're going to replace that 0 with a very small number. We'll just call it E, the variable E. And then what we're going to do is we're going to still do our table with this variable E in here. And at the end, we're going to allow that value of E to approach 0 and see if we get any sign changes. All right. So here's an example. S to the 5th, 2s squared, 2s cubed, 4s squared, 11s plus 10. Two necessary but insufficient conditions. Is this a stable system? We don't know, but do we get any sign changes in the polynomial? Nope. Do we have any term that vanishes? Oh, they're all there. So we know that at least it has a chance of being a stable system. Now I'm going to do Routh-Hurwitz. So I grab my coefficients. Now I start calculating B1. Uh-oh. B1 is going to result in a 0. But I don't know if I need to substitute E yet, because I've got to check to see if B2 is 0. Is B2 0? Yes, sir.
How do you know how many like C1, C1, C2 are supposed to have? Because in this case, you don't have a D2 in this one.
Excellent question. So the question for TV land people is, how do you know how many B's or C's do we need? So the way that you answer that question is, if we wanted to calculate B3, we have to go one column to the right. Those are a bunch of zeros to grab a column. When we do the determinant, we're going to have, isn't that always going to be equal to 0? When you have a column of zeros, there is no coefficients there is no terms that you need to calculate. So once you get over here and there are no more numbers, you don't have to keep calculating anymore, because it's always going to be 0. Because I could keep going on and forever, but we know that these are always going to be 0. So there's no point in calculating. Okay. So generally speaking, if you have numbers here, but zeros here, you don't have to do those extra calculations. And remember, it always goes down by 1 every 2. So you can see I've got 2 here. I dropped 1 position. I have 2 here. I dropped 1 position.
But your top row is to go out another set of numbers.
Exactly. I need a B3 and a C3. Yep. Because I could calculate those terms. Okay. So I've got B1 and B2. B2 is not 0, right? It's 6. So B1, now I would go ahead and calculate my value of E. So I'm going to substitute that in. Now I'm going to go and calculate C1 and C2 using the variable E. And let me get rid of this stuff. So, oops. We'll make it worse, make it better. So C1 now becomes able to calculate, because I'm not dividing by 0. I'm dividing by a variable. It's a small number, but it's still a variable. That's my C1 term. Here's my C2 term, right? So my C2 term is just going to be the 10. Go down to my next row by substituting in. And this is when it can be complicated to calculate the coefficients, because D1, you can see, it's going to be kind of a mess. But with a little algebra, you can do it. Does anybody need to see this out, how to calculate this to get a simplified form? Yes? Yeah, we calculated this out equal to 0. We can't let it equal to 0, because once we have a 0 here, that would be undefined, wouldn't it? So let's go ahead and take a picture of this. Bring up whiteboard. Okay. All right, so first thing I'm gonna do is I'm gonna invert and multiply and then do the quadratic. So D1 is gonna be equal to E or negative E over 4E minus 12. Everybody okay with that? I just inverted and multiplied, no big deal. Now I'm gonna do the determinant. So I have 6 times 4E minus 12 all over E minus E, not E over 10, E times 10. 10E, correct? Hopefully you all can see that that cancels with the one that multiplies out. So that becomes minus 6. Oh no, was it minus 6 or plus 6? Minus 6, yeah. Wait a minute. Why am I getting a positive 6 here? I think that should be a minus 6 here. Well, just let's continue on and let's see. So that's a minus 6. And then I have my, let's see, negative 10. So I have 10E squared when I multiply those out. And then I have over 4E to the minus 12. And then I just divide by 2, right? So I have 5E squared over 2E minus 6. So I get these sign changes backwards, I believe. Okay. So we swap those around. I don't think it's going to change our results. We do minus and plus because when we do our last calculation, we're just going to end up with 10, right? We're going to end up with that final number. So now we let E go really, really small, approaching 0. All right, so plus 0 doesn't really have a number. We're going to allow it to approach 0. We're going to assume it approaches from positive number. So this is plus. When I allow E to approach a small number, 0, what happens to 4E minus 12 over E? What does that work out to be? It's going to approach infinity, but does it approach positive infinity or negative infinity? Because 4E goes to 0, minus 12 comes a negative number, doesn't it? And this one, hopefully from the same approach, 5E squared, which is 5 times 0, is going to be a positive, approaching it from a positive angle. This is going to be 0, so we have 5E squared divided by minus 6, negative number, positive. Yes, sir. No, I'm writing right here. Okay. Those are our coefficients, the 2 sign changes. If we approach it from a less than perspective, E less than 0, we would still end up with the 2 sign changes, but I always do that. So we have 2 poles in the right half plane. Okay. That's only if you have a 0 in the first column. Check it with MATLAB. What do you know? Plus and plus. 2 poles in the right half plane. Okay. And here's the pole 0 map. Let me get this out of the way so you can see those 2 poles in the right half plane. All right, an entire case, or the case when we have a entire row of zeros. So again, we can't just go ahead and replace that with E because we're going to have 1 divided by E times 0. It's still going to end up with 0, isn't it? It's still going to cause us problems moving forward. So the way that we do that is we're gonna use the row just above the row of zeros to get us our coefficients. That row just above is called the auxiliary polynomial. And it's actually gonna be really helpful to us, and we'll see why in a minute. So we take that auxiliary polynomial, and then we take the derivative of that with respect to 0, and that gives us our coefficients for our row of zeros. Okay? You have three possible outcomes. You have symmetric and purely real. So when you do when you have an entire row of zeros, you can have poles here and here. You can have these, and this is the only one I've ever found. I've never found a case when they're symmetric and purely real. I've always found to be symmetric and purely imaginary. And then you can have the third case. The one we're only going to worry about in this class is here in the middle, okay? When you have poles on the j omega axis. So let's do this one. S to the fourth, s cubed, 3s squared plus 2s plus 2. Here's our Routh-Hurwitz. We start off with S4. We grab our coefficients. You're probably getting bored with me showing how to build those. Now I solve for B1. And then I solve for B2. Everybody see how we get that? Let me just, if you can't remember how to get these, to do the determinants, because you all said that you may not have seen that previously. -1/1, the determinant of this is equal to, you take these two, multiply them together, and then you subtract the multiplication of those two. So that equals -1/1, which is 1, times -1, which is +1, okay? That's how you do the determinant one. So I have B1 and B2. I have 1, 2. Uh-oh, I'm in a problem here because I can see that I have exactly the same numbers. So when I do my determinant, I'm going to end up with a 0, aren't I? I know 1 times 2 minus 1 times 2 is going to be equal to 0. And because, as what Wyatt said earlier, every 2 rows, I'm going to get rid of that term. I know that that term is going to be C2 is going to be 0. So I'm going to end up with a row of zeros. So what I need to do is go back to this s squared row. That's my auxiliary. And notice this is x squared, right? So how do I build my auxiliary equation? I recognize this is s squared. So this is 1 times s squared. What's the 2 going to be equal to? Or how do I use the 2? Well, remember when we did the Routh-Hurwitz method? We grabbed this one, and then we skipped. And then we grabbed that one, and then we skipped. So we're skipping the S1 coefficient, and this is 2 times S0. Everybody understand that? That's really important. This is not S1 S to the 1, it's S to the 0. So my auxiliary equation is equal to S squared plus 2. Now to go from S squared to S1, I just take the derivative of that. And I'll just show that over here. So I've already got it typed out. Reason to show it again. So I take the derivative of that, and the derivative of my auxiliary equation with respect to S is just 2S. So now I'm going to replace the 0 with a 2. And then I'm going to continue on, and my D1 calculation is right here. Okay? Notice how I've actually calculated D1. I haven't just written it down there because, again, I'm checking my work. So, no sign changes in the first column. So this appears to be a stable system, except I had a row of zeros in here, didn't I? That row of zeros, if you recall from here, when I had those 3 cases, is shown right here. With poles on the j omega axis, What kind of stability do I have? Marginally stable system, right? This is marginally stable. So when I run through my work, no sign changes, no poles in the right-hand half plane, but I do have a row of zeros, which determines it is marginally stable. And if I take the auxiliary polynomial, s squared plus 2, and set that equal to 0, s equals plus or minus j square root of 2, right? Those are the roots of the auxiliary polynomial. Well, let's check MATLAB and see what MATLAB says. MATLAB says it's not an unstable system. Do you see any positive numbers here? You have zeros, but they're not positive numbers. So that's indicative of plus or minus J2. So the Ruth-Hurwitz told us what a system would be. It's marginally stable. Okay, so when you have a row of zeros, the system, we'll just say in this class, it's going to be marginally stable. Here's our pole zero map. There are your two poles on the J omega axis. All right, now let's do some design, because that's the real purpose of doing Ruth-Hurwitz. So now I've got a system, a block diagram, and I got to do a little block diagram math because I need my characteristic equation, which is the numerator of the denominator, right? So I need this part. That's the numerator that I need. So I've got to go ahead and combine that. So, well, let's just do it out really quickly so that nobody sees that I'm doing anything too crazy here. I'm going to go ahead and solve for the characteristic equation. So G is equal to K over S times S plus 7 times S plus 11. This is unity feedback, so H is equal to 1 all over 1 plus G. Times H, which is equal to 1. Invert and multiply. I end up with K over S squared plus 7S times S plus 11 plus K, right? I'm going to FOIL that. So I have K over S cubed plus 7S times S is 7S squared plus 11S squared, 18 S squared plus 77 S plus K. That's in the characteristic equation that I end up, that's the transfer function that I end up with. This here is my characteristic equation. That's my denominator term. That's what I need. So I go back here. There's my transfer function. It checks what I got. Now I'm going to go ahead and build my table. So again, here are my coefficients, 1, 77, 18, and K. Now I can't put this into MATLAB, can I? Can't put this into MATLAB because I have a variable, so MATLAB can't give me the roots, but I can do Ruth-Hurwitz. So here's B1. And we know that B2 is going to be 0 because there's a row of zeros here. Now, I'm going to continue to build C1 and check my work, and I can see that that value equals K. How do I determine a range of K greater than 0 so that my system is going to be stable? All these have to be positive numbers, don't they? Right? But they all need to be positive. So that right there tells me that K had better be greater than or equal to 0. This last one right here, if I want that to be a positive number, K is going to be greater than 0. Also, 1386 minus K divided by 18 also has to be greater than or equal to 0, doesn't it? Anybody know how to do the algebra for that? It's pretty easy. Multiply both sides by 18. Now, there's a couple ways you can do this. You can move the k to the other side. But you got to be very careful because when you start messing around, you can get really goofy numbers. So what I end up doing, let me move this over here. Well, actually, I have it over here. K has got to be less than 1386. So let's go back. Let me bring this over here. 1386 minus K over 18. It's got to be greater than or equal to 0. 1386 minus K. It's got to be greater than 0. So now I can drag K to the other side. So K has got to be less than or equal to 1386. Be very careful when you multiply an inequality by a negative number, it actually swaps the inequality around. You all remember that from algebra? That's an oddball one. You may or may not have ever seen that. But if you bring the K to the other side, like I did over here, no big deal. If you left the K on the other side and then you just multiplied by -1, the equality sign has to swap directions. So K has to be less than 1386. So in this case, K had darn well better be greater than 0, but also less than 1386. Okay? Questions on that? Yes, sir. What's your transfer rule? Here. Yeah, this is just algebra. Because I can do this, right? I can do negative K is greater than or equal to negative 1386, right? If I just did algebra. And then I multiply both sides by -1, and you think, oh, that's that, right? But when you do inequalities, when you multiply by -1, you actually swap the equality around too. So it's not equal to, it's greater than. And when you multiply a -1 by greater than, you become less than. Wacky algebra. It's the only thing I can think of how to describe it, but that's just an algebra rule. So the rule that I said was, if you can, just bring K to this side. So 1386 is going to be equal to or greater than K, right? I would not suggest doing this because more often than not, you're going to forget the equality, right? Like how many people here would have actually changed the equality? Be honest. You would have? Really? I think you're giving yourself more credit. Very few people have done this. I'm just saying if you did a polar survey, this is not something that you often see. So, yeah. In algebra, you hardly ever do greater than or equal, less than, right? You almost always do equals. So this is a little bit where doing algebra with inequalities makes it a little harder. 5 minutes. Go. Then I can let you out early if you want. Because after this will be on our next exam, which will be not the Wednesday after break, but the Wednesday after that. Doing it all in your head, Aaron? Ah. Well, the one way you'll guarantee you won't learn how to do it is by not trying, right? Fair enough. Here, I'll be magnanimous. I'll give you our Ruth Hurwitz tabulation. 1K plus 2, 3K, 4. You only have 1B to calculate, right? And then 1C to calculate. Because we know this is going to be 0. Anything to the right of that's going to be 0. So now do your Ruth Hurwitz. Solve for B. Couple more minutes. So I had those backwards. Write those the right way. All right, here's what I get for B. So just putting in the form. And then I know that C, I'm not ready to calculate it yet, but I want to make sure that I have a stable system. So I know these all have to be plus numbers. So as long as B and C are greater than or equal to 0, then I'm going to result in a stable system. So I'm really going to focus on this term here and making sure that that is greater than 0. So -1 over 3k times 4 minus 3k squared minus 6k has got to be greater than or equal to 0, correct? I can multiply both sides by 3k over -1. That term's gone. And now I have 4 minus 3k squared minus 6k left over. So I'm going to solve for the roots of this equation because I know that that's going to be equal to 0. When I did that, I ended up with k plus 2.53 and k minus 0.53 just by doing the roots in MATLAB. And I know that k has to be a positive number. Why? Because, well, I actually don't need to. I know it needs to be a positive number because right here, right, that has to be indicating that's a positive number. So I know that 3k has to be greater than 0. So I know that at the very least, k is going to be greater than 0. So this one here, right, got to get rid of it. And so now I'm going to use my value of k, my root of equal to 2.53, which is my value that I'm going to have, and I'm going to substitute that into that equation. And so when I do that, when k equals 2.53, this row is going to be equal to a row of zeros. Okay? So if k is greater than or equal then to 2.53, then I get a stable system. Because I don't end up with a row of zeros here, and I know that that 4 is going to end up over there. So k has to be greater than 0 over here, but over here, it also has to be greater than 0, than 2.53. Otherwise, that's going to be less than 0. So that's what I solve for by doing the roots. So my value of k is going to be greater than 2.53. So this one's a little harder than the previous one because you had a polynomial with our value of k. So all you need to do with our polynomial is just do root finding. And then you just look at other conditions. Over here, k has to be greater than 0 in row 2. And then in B, it has to be greater than 2.53 to make sure it's the system. So let's check. Let's check with MATLAB. So we've got s cubed plus 3k, s squared plus k plus 2. So let's go ahead and solve for the roots of MATLAB. And I did that already for you, right? So this is 1, 3 times k, k plus 2, and 4, right? Those are the coefficients of the polynomial here. 1, 3k, k plus 2, and 4. And I've already defined k to be equal to I said 0.5275. And then I plug that in, and then I hit the roots. Why is this not displaying? Oops. Guess I got to scroll this way. I want to scroll down. Sorry about that, folks. Here. And when I check it, oops, got to annotate. That's in the right hand, our left-hand half plane. These are zeros. So that tells me when I do a pole 0 map, and let's see if I can do the transfer function here. Stop this. So I'm going to do my system is going to be equal to my transfer function. I'm just going to put 1 in the numerator, and in the denominator, I'm going to have let's see, I've got 1, 3 times k plus 2, 4. Oops. I have to put a comma. All right, so that's my transfer function. And then if I do a PZ map of my system, we should be able to see, if it ever brings it up, it's coming out. Going on. Oh, there it is. And it's really hard to see, but I'll annotate so you can see. Here's over here, which is in the left-hand half plane. And right on the J omega axis, because you can see the 0 there, are the 2 marginally stable poles. So this is a marginally stable system. So as long as K is greater than that value, then we have a stable system. Okay. So one was limited because we didn't end up with a positive value. The other one is because we want to make sure that with our roots are greater than 0. So we stay right there. Yes, sir. Which part? Yep. I said it incorrectly. It's got to be 0.53. Oops, let me clear the annotation. Sorry. Clear. It's supposed to be. Doesn't want to erase anymore. Oh, there we go. So when I did my roots here, okay, my roots are, my K value is going to be equal to, I have negative 2.53 or 0.53. This has to be greater than 0, right? So if I plug in 2.53, is 3 times K going to be greater than 0? 3 times negative 2.53, would that be greater than 0? No. So I can't be here. This tells me that at least K has to be greater than 0, right? That one's in the trash. The other one over here says this also has to be greater than or equal to 0. And so when I set the roots up, I saw that if K is equal to 0.53, I get it equal to 0. So I've got to be greater than 0.53. Can't go negative, because if I go negative, this is gone, right? So I've got to be greater than 0.53 and still have a stable system.
That makes sense.
Yeah, I wrote it incorrectly. It's 0.53. Yeah, sorry about that. It's got to be greater than 0.53. So if you get one where you have a polynomial, you just go ahead and do the roots function. And
you cross up a minus 0.53, that's 0, you subtract it to 0.53 the other side.
right. Yeah, I put down the wrong one, but you can even see the value of K I put in here. I said 0.53, but it's actually in MATLAB, it's 0.5275. So you can just keep it a little more accurate. Questions on Ruth Hurwitz stuff? Because essentially, oh, yes, sir. Yes. So Tuesday, we get back from break. So you actually want an extra day for the homework, is that what you're saying? For both of those?
Because I know I'm just making my.
I guess I can move them back to Tuesday, Thursday, unless anybody has any heartburn with that. So move the Tuesday to Thursday and the Thursday to Tuesday. Yeah, that's fine. Any other questions or comments? That was the last one I just posted. And then the one before that was the first order and second order stuff. That one's been posted for a little while, so hopefully you're almost done with that one. The Ruth Hurwitz one I just posted on Tuesday. All right, any other questions? All right, we'll have a safe break. Don't have too much fun. Want to see you back here in one piece, safe and sound. And that's it. Take care, everyone. Have a great day.
Enjoy break, Paul.
Thank you, Mason.